Now let's take a look at our second important mathematical tool. That is to say, non-dimensionalization. Whether we're solving differential equations analytically or numerically, non-dimensionalizing them can be a really important step that can help us out in solving equations for sure, but it also lends insight, as we'll see in a second. All right, so first of all, what is a dimension? Well, many of the quantities that we observe in our world are not just floating around as numbers in the raw, as it were, but instead are measuring some quantity of something. So for instance, the distance from here to here is a length. The weight of an object, like this rag, is a force, or its mass is a mass. So in that case, each quantity has a magnitude, sure, but it also has a dimension. Dimensions like length, force, or mass. Now note that a unit is not the exact same thing as a dimension. Both a centimeter and a league are units that are different, but they are both units representing the dimension of length. Two things with the same dimension can be added, even if they don't have the same unit. On the other hand, any two dimension-full quantities can be multiplied. Lastly, some kinds of functions only take dimensionless arguments. A good example is the exponential function. It doesn't make sense to think of the exponential of a lengthful quantity. And that's actually relatively clear if you think about the exponential as being a power series. That power series involves every power of the argument of the exponential. But different powers, so for instance, length to the first power, length to the second power, length to the third power, and so on and so forth, are different dimensions and therefore cannot be added. Okay, so with all of that sort of precursor work about dimensions themselves out of the way, what's our job when we're thinking about differential equations? Well, we can often make our lives easier by finding particular reference quantities that are embedded in the constants that come from the problem. And to figure this out, let's just give a really simple example to start. So let's say example 1. Imagine throwing a ball upwards with speed v. Now, given this setup, we could ask all kinds of questions. What's the maximum height that the ball reaches? How long is the ball in the air? And so on and so forth. To start, let's actually just write our Newton's second law equation. In this case, it's not too hard. I'm going to say that all of our motion happens in the y direction. And so what we get here is m times y double prime is equal to, well, in this case, the force is constant. It's just going to be minus mg. Now, whenever we do this non-dimensionalization procedure, it's often a good idea to move the m over to the other side, which in this case would be sensible anyway because it cancels with the m on the right-hand side. So let's do that. This implies that y double prime is equal to minus g. Wonderful. All right, as I said, we want to find reference quantities in the problem. And in particular, because we're looking for a trajectory, which is a function that takes an input with dimensions of time and produces an output with dimensions of length, it would be nice if we could find both a reference time and a reference length in the problem. Now, what are our constants that we have to work with? Well, in this case, we have exactly two of them. First, we have v, and second, we have g. These are the only things that determine the trajectory in this case. I'm going to assume that the ball starts, by the way, at a height of 0, such that that doesn't give us any new constant. All right, so how can I combine these constants to get length and time? Well, a little bit of trial and error would be in order, but you'll see that you can get a length if you take v squared over g. This is units of meters squared over seconds squared in the numerator. And then this is units of, or I should say dimensions of meters per second squared. Actually, I guess that is a unit. Meters per second squared in the denominator, which cancels out to meters. If we want a time, we can get the following. Well, in this case, we're going to just want V over G. Now the meters will cancel, but we'll get meters per second and meters per second squared. That'll kick 1 power of seconds to the numerator. So we're all good. All right, now let's engage in the non-dimensionalization procedure. Instead of using our variables that we have from the start, namely y and t, we want to rewrite the equation in terms of completely non-dimensional variables. What would be a good candidate? Well, let's just create a new variable. I'll call it chi. And chi will be y divided by whatever the reference quantity is that has the same dimension as y, namely L ref. Okay, so this is going to be y over v squared over g. Similarly, we need a non-dimensionalized version of time, which I'll call tau. Tau will just be t divided by whatever the reference quantity is that has the dimensions of time, namely t ref. So this is going to be t over v over g. Great. Now I want to take my differential equation for y and rewrite it as a differential equation in terms of chi. But that's a little bit more complicated than it seems, because I don't want to take derivatives of chi with respect to t. I want to take derivatives of chi with respect to tau, because I want to think of this non-dimensional variable being a function of this non-dimensional variable. How are we going to do that? Well, it's actually not too bad. I have on the left-hand side originally d squared y dt squared. And because I can write this in terms of constants, I can make my life actually quite easy. This is the same as d squared of, well, what is it? V squared over g times chi. And then it's d t squared. But t squared is the same as v over g times tau squared. All right, let's bring all of the constants outside. In the numerator, I'm pulling out a v squared over g. In the denominator, because of this squared here, I'm pulling out a v squared over g squared. Then I'll get d squared chi d tau squared. Now, to be clear that I'm not using the same t derivatives, but rather tau derivatives, I'll use prime notation for derivatives with respect to tau. After we simplify everything, I just get g chi double prime of tau. Wonderful. So now I can take this was the same as y dot dot, and stick it into my equation. So now all of that above implies that g chi double prime of tau is equal to minus g. If I cancel the g's on both sides, I now have a dimensionless equation. Chi double prime of tau is equal to minus 1. All right. Now, you can go ahead and solve this equation. It's not really a huge improvement over solving this equation in this case, because I've chosen such a simple example. But let's go ahead and do it. So we're looking for a function whose second derivative is minus 1. That definitely tells me that I need minus 1/2 tau squared as the quadratic term in this parabola. So I should say chi of tau is equal to this. Now, what should be the linear term? To figure that out, we need to also note that we know what chi prime is at tau equals 0. That's because we know that y prime, or y dot, I should say, at t equals 0 is v. We threw the ball upwards with a speed v. That gives us our initial condition for velocity. All right, so if that's the case, tau equals 0 is the same point in non-dimensional time as t equals 0, since tau and t differ only by a constant. So this is going to be v, but because I'm taking chi prime, there's going to be some non-dimensionalization in there. So maybe let's go work that out over up here. What we would have for y dot is, in that case, we are looking at dy dt, which is the same as dv over g times chi over and sorry, that should have been dv squared over g times chi, dv over g times tau, which is, by just pulling out the constants and canceling the g's, equal to v times chi prime of tau. Good. So chi prime of tau is equal to chi prime of tau equals 0 is equal to y dot of t equals 0 divided by v. But y dot of t equals 0 was equal to v. So this is just equal to 1. All right, good. That gives us that our linear term here should be just tau, so that when we take the derivative once, the linear term is going to give us a 1. Lastly, at t equals 0, we assumed that we were at a height of 0. So there should be no constant added in this case. So I could also rewrite this if I'd like. This is tau times minus half tau plus 1. Great. All right, so now I get to benefit from what I did before. Because oftentimes, when we non-dimensionalize things, we've actually done a lot of our work by the time we find the reference quantities. And what I mean by that is the following. If I ask a question like, how high does the ball go? How long is it in the air approximately? Oftentimes the answer is within an order of magnitude of the reference quantity itself. The reference quantity does a good job of estimating the sort of important timescales for the problem, or length scales. So how high does the ball go? I think a pretty good guess would be that it goes exactly v squared over g. It turns out that actually the max height, which you can find from this equation here, is v squared over 2g. So we were only off by a factor of 2. Pretty good if we're just looking for a simple estimation. Similarly, the amount of time that it's in the air, well, in this case, we might guess that it's v over g, and that turns out to be also off by a factor of 2. We actually can see that right away. The second time that this chi function intercepts the x-axis is going to be at tau equals 2. So this is going to be 2v over g. Wonderful. So this really gives us the upshot. Why should we care about non-dimensionalization? Well, one of the big reasons is exactly this. It tells us about what kind of time and length scales are going to be important for the problem. There are other reasons too, and I'll get to those in just a moment after I've cleaned off the board. All right, let's use our new non-dimensionalization techniques to treat a sort of classic physics 100 level problem. So we'll look at the case of a mass sliding on a frictionless ramp that makes an angle of theta with the horizontal. It's being pulled down the ramp by a force F external that points directly down the ramp, and it's attached to the top of the ramp by a spring with spring constant K. We'll say the equilibrium length of the spring constant, or of the spring, is 0, just to keep our lives simple. Now, there are lots of different ways to do this problem. One good way is to define a new set of directions. We could call them the u direction and the v direction, and we'll note that things don't get very interesting in the v direction and focus only on the u direction. Now, typically, once we draw the free body diagram for this problem, which I encourage you to do on your own, the next step is to write down Newton's second law for every direction and for every mass. We only have one mass here, and we only care about the u direction. So let's go ahead and do that. Now, I'm going to move the m to the other side. So what I'll get is u double dot, u being the length that it's gone down the ramp, is equal to, well, we have a contribution due to F external. That's going to be F external's magnitude over m, And then we have a g times, as it turns out, the sine of theta. And then we have minus ku squared. That's the force from the spring. And sorry about that, that's the force, but I need the acceleration because I divided by m. Wonderful. So this is the problem that we need to work out. In general, it would be totally doable to now start guessing the reference length and reference time. Those are always the quantities that we need because we're trying to solve, again, for a variable that takes an object with dimensions of time and outputs an object with dimensions of length. So, okay, we could do this by guess and check. But there's actually another way, and this is something I want to show you in case you ever want to be systematic about things. It also turns out that this will help us categorize different kinds of problems using what's called dimensional analysis. So we're going to define so first of all, I should say, we're going to list all of the constants in the problem. The rule of thumb is that if two constants only ever appear as a product or a quotient, we're going to count them as a single constant. So what do we have here? Well, it looks like we have f over m, that's going to be 1. We have g, that's going to be 2. We have, and I'll just say sine theta is another one because theta never appears except as sine theta in this expression. So we'll say sine theta is 3. We have k over m, that's going to be 4. Lastly, I failed to give initial conditions here, but let's imagine that this block starts from rest. And let's say also at u equals 0. So we don't have any initial conditions that give us new constants. All right, so let me make sure that that's clear. U at t equals 0 equals 0. U dot at t equals 0 is also equal to 0. Good. Well, let's think in general about what happens if we have a constant a and a constant b. And suppose that a has some, let's say it has dimensions of length to the r1 times time to the s1. And let's suppose that b has dimensions, length to the r2 time to the s2. Now, let's imagine that we want to guess that our reference length or reference time can be obtained by taking a to some power and multiplying by b to some power. Those powers are allowed to be negative as well. Well, we would have a to the m, b to the n. What are the dimensions of this entire object? Let's write them out down here. The dimensions are, well, because of the way that exponentiation works, I'm going to take m and multiply it by these two dimensions. So I'm going to get length to the r1 times m from a to the m, and time to the s1 times m. But I'm also going to get length and time from b. So in the end, I will get length to the m times r1 plus n times r2 times time to the ms1 plus ns2. Now, if I wanted something that had dimensions of length, I would be demanding that a to the m times b to the n has dimensions of length to the 1, for instance, times time to the 0. That would give me a reference length. So let's suppose we want this to be equal to length to the 1 times time to the 0. That means we're trying to solve the system of linear equations m r1 plus n r2 is equal to, well, this exponent needs to equal this exponent, so that's equal to 1. And ms1 plus ns2 is equal to 0. And we know how to solve systems of linear equations in a systematic way because we've, at this point, got linear algebra under our belt. The answer is that we can set up a matrix that solves this for us if we augment it. Okay, so I'm going to define my matrix D, and we'll use this matrix D for everything that follows. The rows of D are going to correspond to all of the possible units, or dimensions, I should say, that make up our constants. Now, in both my cooked up example with A and B, and in the problem to the left, the only ones that we need to care about are length and time. But in general, you might have others like mass, charge, temperature. It really just depends on the problem. So in this case, let me note that I'm going to have length and time in my matrix. Okay, now for the columns, it's going to be all of the different constants that I have in my problem. So let's do the problem on the left. So our constants are f external over m, g. Now actually, sine theta does not need to be included. The reason for that is actually very simple. Sine theta is already dimensionless, so it's never going to contribute to the dimensions of the problem. I'm certainly allowed to add a column full of zeros, but as we'll see, it doesn't actually do anything for us. So I'm going to omit sine theta, and then lastly, I'll have k over m. Now, what are all of the dimensions of these things? The dimensions of f external over m are acceleration. So acceleration is given by length times, or divided by time squared, or length times time to the minus 2. The rule is I'm going to go down this column and fill in what the exponent of length and time is in my constant. So I have length times time to the minus 2. Good. G also is acceleration. So I have length times time to the minus 2. Lastly, I have k over m. Now, I know that square root k over m is a frequency. In other words, root m over k is a time. So this one has 0 units of length and I screwed up. Screwed up way further back. Now, k over m, I just realized I need to amend something. This is not the force, this is the energy, if I added a half in there. So let's correct that. This should be kmu. In any case, I know that the square root of k over m is a frequency. From, for instance, a section in intro mechanics on springs. So k over m is a frequency squared. Frequency squared is going to give us time to the minus 2, but no units of length. Wonderful. So now, suppose that I want to solve for a particular set of system of equations like this. In particular, suppose that I want to solve for a length, or suppose that I want to solve for a time. I can actually do both at the same time by augmenting this matrix. Now, if you look back to a linear algebra textbook, the way that this is typically represented is by putting a dotted line between the regular part of the matrix D and the augmentation that we want to make. The augmentation of these extra columns are going to have the things that we want to solve for. So in this case, we would love to solve for the reference length, L ref, and we know that L ref has units of length and 0 units of time. And we'd also like to solve for T ref. We're totally allowed to do these at the same time. So this will be a 0 here and a 1 here. And now we would try to row reduce this matrix to find a solution. I'm going to skip the steps here and just provide the solution. So by row reduction. Now here's the completed row reduced matrix. It's not obvious right off the bat how you would use this to get answers to the questions that you wanted. So here's the formula. To find LREF, I would look down column 4. That is the LREF column. This tells me that I'm going to need 1 power of the stuff that comes from row 1 and minus 1 power of the stuff that comes from row 2. Now, row 2 is unambiguous. It only includes k over m. So I'm going to need minus 1 power of k over m. In other words, a power of m over k. But what about from row 1? Well, all it tells me is that my powers of f external over m times 1 times my powers of g times 1, plus my powers of g times 1 are going to equal 1. In other words, there are 2 good choices, at least. I could pick g, so for my LREF, I could pick g times m over k, or I could pick f external over m times m over k, which is equal to f external over k. Either of those would work, as would any combination here. So I could also just pick g to the 1/2 f external over m to the 1/2 times m over k. That's also a possibility. So what this represents in this case is that I don't have a unique reference length. And in fact, that is a common situation when we do dimensional analysis. Meanwhile, for TREF, I read down this column. Here, I see that I need a minus 1/2 of whatever's to the left in row 2. But row 2 is unambiguous. It only includes k over m. So this tells me that TREF is uniquely square root of m over k. Great. All right. Now let me erase the board, clean it up, and we'll talk about all the possibilities for this D dimension matrix. Now it seems from what I just did like finding this dimension matrix D and augmenting it, then row reducing it, is just a really long and cumbersome way of finding the reference quantities that we could just find by hand. Maybe this process is simpler in some situations with lots of constants or something like that, but it's not necessary. That's, of course, true for finding the reference quantities, but it turns out that D gives us more information about the problem than just the reference quantities themselves. So let's first concentrate on the fact that there are kind of 3 possibilities for D and its augmented form. These are given to us by what's called the Rouchet-Capelli theorem, which you may have learned about in linear algebra, and it just tells us whether or not a system of equations encoded in an augmented matrix has a solution. And if it has a solution, how many it has. All right, so the 3 possibilities for D, I've given specific names. D and its augmented matrix could be dimensionally underdetermined, and this means that the rank of D is less than the rank of D augmented. And what you'll see is that that means that the system of equations simply doesn't have a solution. Or when we want to think about it in terms of the constants in the problem, it means that there's no way to combine the constants in our problem to give both a reference length and a reference time. That's possible, and what it means we'll get to in a moment. The next possibility is that we have a system which is dimensionally well determined. This means that the rank of D and the rank of D augmented are the same, and that the rank of D is equal to the number of columns of D. Now, in this case, we have precisely the number of constants that we need in order to make all of our reference quantities, and no more. So all of our reference quantities are unique. This was the case in the first problem that we looked at, where we launched a ball upwards with speed v, and it was pulled down by gravity with gravitational acceleration g. So a dimensionally well-determined problem has sort of exactly the correct number of constants. That's the way to think about it. Lastly, we have dimensionally over-determined problems. In this case, the rank of D is equal to the rank of D augmented. Notice that since D augmented includes D, the rank of D augmented could never be less than the rank of D. So this is actually all of the possibilities. And the rank of D is greater than the number of columns. I'm sorry, is less than the number of columns. All right, and we notice that this is the case here. Remember that in its row-reduced form, our D augmented in this case, row reduced to 1, 1, 0, 0, 0, 1 in the D part, and then the augmented part gave us 1, minus 1, 0, minus half. Okay, so recall that the rank is the number of linearly independent columns. Notice that the maximum number of linearly independent columns is 2 in this case, because we only have 2 rows. And we have 1, 0 here and 0, 1 here. So we have 2 linearly independent columns, say 1 and 3. But column 2 is not linearly independent from column 1. It's exactly the same as column 1. Similarly, augmenting the matrix does increase the rank because we've already hit the maximum number of possible linearly independent columns. All right, so in this case, the rank is 2, but the number of columns of D is 3. And that exactly means that we had 1 spare constant. For instance, if we chose to make L ref using G, then F external over M ended up as a spare constant. So in this case, we have constants to spare. And the number of, we call them, I guess let's just say for the time being, extra constants, is exactly equal to the number of columns of D minus the rank of D. Great. Okay, so this is a big step in performing a dimensional analysis, figuring out exactly how many of these things there are. So let's actually continue with our example from over here and write down what the solution was in our non-dimensionalized units. So in this case, let's choose LREF. Remember that this is a choice because the LREF was not unique. Let's choose LREF is equal to mg over k. And similarly, we know that tref is equal to square root of m over k. If we define our non-dimensionalized length as xi and our non-dimensionalized time as tau, then we find the solution is xi of tau is equal to f external over mg plus sine theta times 1 minus cosine of tau. Now notice that because the left-hand side here, xi of tau, is dimensionless, the right-hand side must also be dimensionless. So anytime f external over m appears, it must be canceled out by something with the same units, or the same dimensions. In this case, g is the natural thing. So it makes sense to take this combination, which must appear like this, and give it a name. This is called alpha. Or I suppose we can call it alpha. And alpha is our first example of what's called a dimensionless parameter or dimensionless constant. Now the number of extra constants is just exactly the same as the number of dimensionless parameters, and that's because for every extra constant, we can divide by the reference quantities in some combination to come up with a dimensionless parameter or dimensionless constant. So this is the same as the number of, let me say, linearly independent. We can, of course, combine them into new dimensionless constants. And that's really important. Now, in our first case, where we were dealing with a ball thrown up in the air and then pulled back down due to gravity, we found that the solution always looked like a downward-facing parabola. And once we non-dimensionalized, the coefficients of that parabola were fixed. In some sense, the non-dimensionalized version of the problem has 0 degrees of freedom. It always looks exactly the same if we plot it in non-dimensionalized units. On the other hand, this problem with one dimensionless parameter that we get from non-dimensionalization can look different when we change dimensionless parameters. This problem, of course, actually has 2 dimensionless parameters because we started out with 1 in sine of theta. So in other words, the only way that we can change the form of the solution of this problem is we could change alpha or we could change sine of theta. Other than that, in non-dimensional variables, the solution always looks exactly the same. Okay, so that answers the question of why would we go through all of this dimensional analysis in the first place? Well, as it turns out, the dimensional analysis doesn't just give us important reference quantities that let us guess the important time or length scales of the problem. Rather, it also tells us about the structure of the solution, whether or not the solution is always the same for any values of the constants as soon as we non-dimensionalize, or whether or not the solution can look different for different values of those constants. So this is just a sort of bite-sized look at the way that dimensional analysis works in really complicated problems. We'll keep working with dimensional analysis and seeing ways that it's important as we go through the course. I encourage you, anytime you solve a problem, to consider non-dimensionalizing it. Sometimes looking at both the dimensionful solution and the dimensionless solution can give you a lot of clarity. And in fact, going through the formulaic algorithm of finding D, finding its augmented form, and row reducing it can also give you a lot of clarity. This is also a great way to do numerical problems. Now here at Reed, in our sophomore numerical methods lab, students learn how to use the Verlet algorithm to solve Newton's second law type problems. You might ask, when you're doing the Verlet algorithm to figure out the trajectory of a particle, what should be the time step that you use? How small should those time steps be? You see students doing a lot of guesswork in order to figure out what makes sense. The correct answer is always to non-dimensionalize your problem, and then in the dimensionless version of the problem, then you can pick a quantity that's much smaller than 1. In other words, you want to pick a time step that's much smaller than your reference time. Similarly, if you were looking at approximations that involved the length, you would want to pick quantities that made sense based on your reference length. So non-dimensionalization is equally important if you're going to use approximate methods to find solutions to problems. Lastly, I'll say that one thing that can often be really useful in solving problems, especially analytically, is looking at limiting cases of a problem. When we're looking at limiting cases, we often want to make some quantity very big or very small. But the question always arises, what does it mean for a quantity to be very big or very small? 1 centimeter is very large compared to 1 micron, but it's very small compared to 1 kilometer. So what does small or large mean in the context of a given problem? The answer is look at your reference quantities. The reference quantities will tell you. So if you're planning to tailor expand the solution of a problem or something like that, then the reference quantities in the dimensional analysis come in handy there too. I hope you find this stuff useful as we go on, and until I see you in the next one, thanks for watching.